Hello and welcome. My name is Matthias Kümmerer and I'll be presenting our paper Modeling Saliency Dataset Bias. When we look at images, we don't look at all image regions with the same frequency. We fixate some image locations more than others. Saliency models try to predict the average fixation density for a given image. Building good saliency models has applications in compression, layouting and design, can gain insights about efficient resource allocation, and has interesting connections to cognitive science and neuroscience. On the MIT 300 dataset, the most important saliency benchmark, performance seemed to saturate in the last years, begging the question whether we are done with spatial saliency, whether we are overfitting to the benchmark dataset, and whether it's still worth to keep working on saliency modeling. These questions motivated us to test how well prediction performance on a popular dataset like MIT 300 transfers to other images that one might encounter in practice. To that end, we construct a saliency model which extends the deep gaze architecture. An image is processed by a feature extractor, which unlike in previous deep gaze models, now is a multi-scale feature extractor. Some of the scales are defined in total image resolution, others in pixel per degree of visual angle. After we extract activations from clip in Dino version 2, we average them across scales with learnable averaging weights. The result is decoded by a small readout network to yield a priority map, which is then post-processed with global scaling, Gauss blurring and additive center bias before it is converted into a fixation density prediction. The model is trained for maximum likelihood on the human fixation data. We include 5 different datasets with human fixation data in our experiments to test how well models generalize from one or multiple dataset to different datasets. We found that when training on one dataset and evaluating on another dataset, we experience a large inter-dataset gap. The usual approach to tackle this is to train on more data. When we train on 4 out of 5 other datasets, generalization performance on the left-out dataset indeed goes up. However, more than half of the inter-dataset gap still remains in the form of a generalization gap. Datasets seem to be inherently different in ways that are hard or impossible to learn from multiple datasets. We hypothesized that few simple biases in the datasets account for most of the generalization gap. To test this, we made the averaging weights, the priority scaling, the Gauss blur size, the center bias, and the center bias weight dataset-specific. Together, that's only about a dozen interpretable parameters, while the bulk of the parameters in the readout network are still shared across datasets. When training with these dataset-dependent bias parameters on 4 datasets and then adapting only the bias parameters to a new dataset, we improved performance on the new datasets massively, closing 78% of the generalization gap. The dataset parameters can be adapted in a data-efficient way with only a few samples. Together, this shows that indeed very few interpretable effects account for most of the generalization gap to new datasets. Coming back to the performance curve on the most important saliency benchmark, our strategy allowed us to improve substantially over the previous state of the art, showing that progress still can be made in saliency prediction. We set a new state of the art on all datasets of the MIT Tuebingen Saliency Benchmark, and not only in the full joint training setting, but also when generalizing and when adapting only the dataset bias parameters. In this case, we again close a large part of the generalization gap. Looking at qualitative results, we see that our model fixes systematic errors of the previous state of the art, such as faces that are turned away in partially occluded objects. This shows that the performance improvements we made matter in practice. But we also find remaining cases of systematic errors, for example low-level pop-out, schematic drawings, and occluded interactions. This demonstrates the need and potential to improve models further. Thank you for your attention. For more details and analysis, please have a look at our paper. If you have questions or comments, you're very welcome to come by at my poster at a poster session here at ICCV or contact me via mail. You might also be interested in checking out our website and GitHub repository. Thank you again.